So do I start?
Nope.
Okay.
Nope. We're starting to populate. Everybody can hear me speaking.
Okay.
And we're gonna let people populate for a couple of minutes before we actually get started. So we have 21 members at this moment, David.
Okay.
I figure we'll start at 4:02. That would allow everybody to get in. Okay, I'm going to mute myself. We're tapped out at 21. You can start anytime you'd like.
Okay. Hello, everybody. On behalf of my colleagues, welcome to the Johns Hopkins University Institute for Assured Autonomy Research Summit. Our keynote speaker this afternoon is Dr. Cynthia Rudin. Cynthia Rudin is the Earl D. McLean Jr. Professor of Computer Science, Electrical and Computer Engineering, Statistical Science, Mathematics, Biostatics, and Bioinformatics at Duke University. She directs the Interpretable Machine Learning Lab, whose goal is to design predictive models that people can understand. Her lab applies machine learning in many areas, such as healthcare, criminal justice, and energy reliability. Professor Rudin holds an undergraduate degree from the University of Buffalo and a PhD from Princeton University. She is the recipient of the 2022 Squirrel AI Award for Artificial Intelligence for the benefit of humanity from the Association for the Advancement of Artificial Intelligence, which is the Nobel Prize of AI. She is also a three-time winner of the Inform's Innovative Applications and Analytics Award and a 2022 Guggenheim Fellow. She is a fellow of the American Statistical Association, the Institute of Mathematical Statistics, and the Association for the Advancement of Artificial Intelligence. Today, Dr. Rudin will talk about do simpler machine learning models exist and how can we find them? Welcome, Cynthia, and over to you.
Thanks, David. I'm going to share my screen here, which you should be able to see. Now, I started working in interpretable machine learning because I was working with the New York City Power Company trying to predict power reliability. That more complex machine learning methods weren't giving me any better predictions than very simple models. And I thought that maybe the problem that I was working on was an anomaly, but it wasn't. Like the same thing kept happening over and over again. So here's another example. So back in 2015, we wrote this article called Interpretable Classification Models for Recidivism Prediction. And in this article, we used the largest public data set on criminal recidivism. So this is over 33,000 people released from prison all in the same year. And we used interpretable machine learning tools to predict whether someone would commit one of a bunch of different kinds of crimes. So these are like misdemeanors, violent crimes, sexual crimes, property crimes, drug crimes, whatever. And what we showed was that we don't actually need a complicated model to predict recidivism. And also that race was actually not a useful variable for predicting recidivism. So recidivism is, will you be arrested for a crime after you're released from prison? And so, race isn't a useful variable for predicting that. And so we were pretty surprised when the ProPublica group came out with their article a few months later that claimed that there is this proprietary model that's used throughout the US justice system, and it relies on race. And we thought, okay, well, first of all, race doesn't even predict recidivism. So, not sure about their conclusions there. And then second, these types of models shouldn't be proprietary because they determine people's freedom. And so we were wondering, like, how accurate is the model that they were talking about, right? So COMPAS, this is a proprietary model. It's widely used in the justice system. How accurate is it? And so we did an experiment where we compared the COMPAS scores from the ProPublica article to, this is in Broward County, Florida. So the scores they were using were from Broward County. And we compared it to an algorithm that we developed at the time that the data set was released. And the algorithm's called Corals. And Corals is a really complicated algorithm, but it produces very, very simple models. And so Corals produced a machine learning model that was so tiny on this data set that it fits into the bottom of a PowerPoint slide. So the model says if you're 19 to 20 years old and you're male, predict arrest. Else if you're 21 to 22 years old and you have 2 to 3 prior offenses, predict arrest, with arrest within 2 years of your COMPAS score calculation. And then else if you have more than 3 priors, predict arrest, and then otherwise predict no arrest. And we thought, okay, that's a really simple formula. Could this really be as accurate as COMPAS? And surprisingly, it was. So here are, these are test results. So this is out of sample results on different folds from 10-fold cross-validation, and the colors are different folds. And what you can see is that these models are about equally accurate, okay? So it's not really clear to me why we need proprietary models in the proprietary model is just as accurate as the one that and we thought, okay, well, can we get any more accuracy? Like, what if we just throw the whole machine learning arsenal at the problem? So we did. And we got essentially the same accuracy. And so some of these methods produce models that are so big that they don't even fit on a PowerPoint slide, whereas the whole Corals model is just right there in the corner of the slide. So, you know, anyway, there was a big debate about the algorithmic fairness of COMPAS, but I think it was all misdirected. I actually think the truth is that we just don't seem to need models like COMPAS at all. Anyway, this is not the only data set where simple models perform well. In fact, this happens very often. So let me show you another example. And this time I'm going to choose a really high stakes example in medicine. So here I'm talking about preventing brain damage in critically ill patients. So let's say that you have an aneurysm and it bursts. So you have like a brain hemorrhage, right? So this is blood that's leaked into your brain. You are not in good shape at that point. You'd go to the hospital, you'd get emergency surgery, you'd be placed in the intensive care unit, and they would put EEG monitors all over your head, and those monitors are detecting for the possibility that you might have a seizure. Now, seizures in these patients are common. They cause brain damage, they cause death, and the only way to detect seizure-like activity is through EEG. These are not patients who are shaking, right? This is all like in the patient's head, right? So I worked with neurologists that to develop a model, and if this was you, and you know you had this happen, there's a chance that if you were in the intensive care units, the doctors would score your risk of seizure using the model we developed, and that model is called the 2 helps 2B score. And that model is so small that it fits in the bottom of a PowerPoint slide, the corner of a PowerPoint slide. Now, the name of the model comes from 2H here. This is 2H, ELPS, and then 2 points for the B, so that the doctors can memorize the whole model just by knowing its name. And the total score just translates into a risk of seizure using the table at the bottom here. Now, this model was designed by an algorithm for interpretable machine learning. So it's just as accurate as black box models, but it's designed by an algorithm where I know it looks like somebody might have made it up, but that's not what happened. This is actually a machine learning model. And the selection of the features here and the different point scores, like the thresholds here and the point scores, all of that was chosen by an algorithm. Now, you can see that it's a sparse generalized additive model here with integer coefficients. That's what this type of model is. And it's actually a hard combinatorial problem to design these things, because you got to figure out like which subset of features work together. Like we started with over 70 features. And so the algorithm had to figure out which subset of features can work together to form a model, to form an accurate predictive model. Now, the nice thing about this model is that unlike black boxes, right, that doctors can decide themselves whether to trust it, right? Interpretability doesn't force you to trust it. It enables you to decide whether or not you want to trust it. Now, also, since the doctors put it into practice, they did a validation study, and they found that it led to a substantial reduction in the duration of EEG monitoring per patient, which allowed the doctors to move the monitors around more efficiently and monitor 2.82 times more patients than they did before, which, according to the doctors, allowed them to reduce brain damage and save lives. And it's, it's actually, like I said, it's actually optimized very carefully using an algorithm for interpretable machine learning that uses cutting planes. All right, so it seems that there's no benefit from complicated models for lots of problems. Now, I've listed here a number of applications that I've worked on, including electrical grid reliability that I told you about, seizure prediction in ICU patients. And for none of these problems did I require a black box model. So it could be like in the case of like the compass example that I gave, that we're using complicated models for high stakes societal decisions when we don't actually need them. Now, in any case, there is a bit of nuance to what I'm saying here, because there's really two fundamentally different types of problems that we encounter. And these are like two totally different fields of machine learning, right? The whole thought process is like night and day between these two data types. So when you're working with these two data types, you actually have to think in a different, it's like you're speaking a foreign language, like it's really quite a different way of thinking. Now, with tabular data, so that's where we have a good representation of the data and all the features are interpretable. Like here's a healthcare example over here. Whereas raw data is like kind of images or sound waves or large amounts of text. And with, that's with raw data. And with raw data, the only type of technique that's working right now is really neural networks. And that doesn't mean that you can't have interpretable models. Like I advocate for interpretable neural networks, but in any case, for raw data, you're stuck with neural networks. Whereas with tabular data, neural networks don't really help. Like from what we can tell, with minor preprocessing, all the methods tend to have similar performance. And that includes neural networks, but also very sparse models. So like even like decision trees and scoring systems. So raw data, it's really fundamentally different. Like it tends to live on very thin manifolds of feature space. So for instance, if you think about the space of natural images, if you just change one pixel in an image, that no longer is a natural image. Like you've actually bumped it off the manifold of natural images. And so it's actually like out of distribution at that point. So it's actually a very different sort of, it's just the whole data type is very different. Now, tabular data is generally not like that. It's usually not that sensitive to changes in the data. Like if I change like exercise and allergies, then that vector could still be realistic. Now, we were wondering, like, why are we not getting any benefit from complicated models here, right? It seems like there should be some benefit to lots of extra complexity, but that doesn't really happen with tabular data. Like, as soon as you start adding more complexity, you just overfit. Now, I have a theory as to why this happens, and it's a very simple theory. And my theory is that there are just lots of good models. So let me explain that a little bit more. So my theory, it's called the Rashomon set theory. And like I said, the Rashomon theory is just that there are just lots of good models for tabular data problems. So for example, if this is like all the models, well, maybe a large number of them are good. Maybe not like half of them, but like a large number of models are good. And this set should be large enough to contain a ball of models, like a ball of good models. And then if the set of simpler models is a good cover for the set of all models, like it's a good cover for it, then the idea is that as long as the set of good models is large enough to contain a big ball, then the set of good models should contain at least one of those simpler models. Okay, so that would sort of guarantee you that you have a good model that's also simple. Now, I think the idea that simpler models is a good cover for the set of all models, I think that's totally reasonable. So for instance, sparse decision trees, those are a good cover for the set of all decision trees, and decision trees are universal approximators. So I actually think this makes sense. So, okay, so let us call this set of good models, we're going to call that the Rashomon set. Obviously Rashomon named after the Japanese movie, right, where you've got a lot of different views of the same, it was actually a murder. And then, none of these witnesses you think are maybe the truth. Like there's no truth, like who knows what actually happened, right? So it's just a lot of good explanations. And so that's why it's called the Rashomon set. So it's all the models that have loss that's close to optimal on the data set. Okay, so now I claim that the Rashomon set is large in many of the types of problems that I consider. Now in this paper with Lesia Semenova and Ron Parr, we did a lot of very computationally heavy experiments. We actually calculated the size of this Rashomon set, or the kind of the ratio of the set of good models to all models. We actually calculated that for like 70 different data sets for decision trees. We did this calculation. And then we tried to correlate the size of the Rashomon set, like the size of this thing or the ratio here of the set of good models to all models. We tried to correlate that with lots of different things. And what we found was really interesting. So we found that large Rashomon sets, so lots of good models, that's correlated with the existence of simpler models, which, okay, fine. You know, I told you why we expect that to happen, so we're good, okay. And we also found that large Rashomon sets are correlated with many different machine learning methods having the same performance. So now, as it turns out, that if you run lots of different, like I'm talking about very different machine learning methods, like you run like boosted decision trees and support vector machines, like models that have very different forms, okay? So if you run these different algorithms, machine learning algorithms, and they all have the same performance, what that means is that those models are all in the same Rashomon set, okay? So in other words, if you run support vector machines and you get and boosting and so on, you have all these very different models and they're all in the same Rashomon set, which means the Rashomon set has to be large enough to accommodate all of these very different models. So the Rashomon set is large. Okay, now the last thing we found was that large Rashomon sets are correlated with more feature and label noise. So these are outcomes, these are problems where the outcome is hard to predict. So for something like criminal recidivism, for instance, it's really hard to predict whether someone's going to commit a crime within 2 years of being released, right? There's so much randomness in that whole process that it creates like an intrinsic level of noisiness to the data. All right, and the implications for this theory, if I'm right, and there are just lots of good models for lots of tabular data problems, right? If I'm right about that, then what it means is that optimizing for simplicity won't actually sacrifice accuracy. Now, this has a lot of really major implications for a lot of high stakes decisions that are made using data in our society that deeply affect people's lives. And this includes criminal justice decisions that determine people's freedom, for loan decisions that determine someone's ability to purchase a home, or for medical decisions that determine life or death, right? Because if I'm right, then for none of these decisions can we justify the use of black box models, right? For none of them. So now this theory reveals why we think we were able to find accurate models for these data sets without losing predictive performance. It's because these data sets probably admit many good models, right? They're all tabular and they'll have noise because we're predicting things that are inherently hard to predict. Okay, so let me go back for a minute to the results of our fact paper, right? Because this result is actually very useful. Okay, so what I'm saying here is that if you run many different machine learning algorithms on the data and you get the same performance, then you can decide whether it's worthwhile to run something more computationally expensive to get a more interpretable model. And I want to tell you about a case where we did this. And I'm going to talk about the data set for the explainable machine learning challenge. Now, FICO gave us this data set about loan decisions, and they said, make a black box and explain it. And the question is whether we need to do that, okay? So take a look at this data set. It's 10,000 loan applicants, lots of information about their credit history. And I thought, could it be a tabular data set where you need a black box? And so I asked my students to do some experiments. So I said, could you please run lots of different black box algorithms on the data set and see if they all perform the same? And the students came back to me in 2 days and they said, yep, they all perform the same. And so at that point, I knew we probably did not need a black box for this data set, right? Now, at the time of the competition, we didn't have methods that are as powerful as the ones we have now. So I get the benefit of telling you about these results after developing these algorithms over the course of 5 years or whatever, and sparing you the details of the first few models that we created and how long it took to do it. So you get to see some 2022 algorithms in action instead. Okay, so the first algorithm I'm going to talk about is fast sparse. And this paper produces sparse additive models, which are an alternative to logistic regression. And it is fast. And I'm going to give credit here to my students, Jiacheng Lu and Chudi Zhang, and then Margot Seltzer, who's my longtime collaborator. All right, so I'm going to tell you about that algorithm. First, I'll tell you a little bit about the data set. So if you run lots of black box algorithms on this data set, the best accuracy you can get is about 73%. Best AUC is about 0.8. Okay, so these are the performance metrics we want to maintain when we switch over to interpretable machine learning. Now, the fast sparse method that I'm going to tell you about takes less than 20 seconds, and its training and test accuracy are right on par with the best of the black boxes here. Okay, so you're not losing any performance. The difference is that on the next slide, I can give you the entire machine learning model from fast sparse, and I can do that because it fits on a PowerPoint slide. All right, so here's the whole model right there. And you just get a score for each of these features. Like you just look up your score for each feature and you just add it up. And that translates into the risk of defaulting on a loan. Okay, so I'm just gonna look at some of the factors here. So let's look at like months since oldest trade open. So here, if your trades were all recent, like they were all in the last 100 months, then you get more risk points than if you had, your trades were more mature. And then like number of satisfactory trades. If you had less than 10 satisfactory trades, you get more risk points. And then like external risk estimate. This seems to be a very important feature, and it's particularly sensitive between values 60 to 80 here. Like you get a lot more risk points if you have a low value of this external risk estimate here. All right. Now, yeah, so that's the whole calculation. You just look up each of your points for each of these different features and you just add it up, and that just translates into a risk for defaulting on a loan. All right, so what's really shocking about this model, besides its simplicity in describing this very difficult data set, like it's a benchmark data set, right, is that it actually finished in under 4 seconds. And it created this model. This is the machine learning model. It created the whole thing in under 4 seconds. And that's how fast this algorithm runs on average. It's usually about 4 seconds. Now, the competition, as I said, they told everyone to create a black box and explain it. And they told us this because they didn't know that it was possible to create a model like this at all. And we did it in under 4 seconds. So let me tell you about the machine learning method that created this really sparse additive model in just a few seconds. And I'm going to put a little math up, so apologies if you don't like math. Don't worry, it'll go away in just a slide or two. All right, so I'm going to start with just plain old sparse logistic regression. So here, I'm going to minimize the logistic loss with L0 regularization. And the L0 term, that's just the number of non-zero elements in the model, non-zero terms in the model. L0 is better than L1, doesn't have the bias of L1 that shows up when you want a really sparse model. And then over here, the model is linear. This is a linear model. And then we're going to just translate just translates into a conditional probability using the usual formula for conditional probabilities for logistic regression. So you just plug your value of f in here, and you get the probability, an estimate of the probability that y equals 1 given x. Okay, so far, all standard stuff, okay? Now, to get a generalized additive model, the simplest way to do that is to transform the variables before you do anything as a pre-processing step. So for instance, if you have age as one of your x variables, then you can transform age into lots of dummy variables. And see, now you've got like a lot more features, right? Because you blew up the feature space. You just have lots of more variables. But now you can create these very flexible functions of age because you're adding up weighted combinations of dummy variables. And when you add up weighted step functions of weighted step functions, you get things like this, which are kind of like really interesting things. So you can kind of create anything, like any shape out of these little step functions, okay? Now, like the vast majority of machine learning algorithms, to minimize this objective, we're going to do some variation of gradient descent. And in particular, we're going to do coordinate descent where you adjust one of these W's at a time. And we're often setting them to 0 because we want models that are sparse. So every iteration, you're going to adjust one of these W's, most of the time setting them to 0, occasionally bringing, switching, which variable we're working on. Okay. So, and yeah, we're going to try lots of feature subsets just to, that seem promising according to this objective. Okay. So we came up with this really fantastic idea. It involved cutting planes and quadratic cuts, and it was really fast for solving the problem. But then we figured out a way to do it that didn't involve cutting planes or quadratic cuts. It was actually much simpler, and it was about 5 times faster. And it involved changing the problem just slightly. So here, instead of using the exponential loss, I'm actually going to switch over to the using the logistic loss here. Instead of using logistic loss, I'm going to switch to exponential loss, which is this guy. And then the only thing that really changes is that there's a couple of 2's that get added in here that weren't there before. And exponential loss is very convenient. It's the same loss function that's used in AdaBoost. And the probabilistic model here is almost the same as logistic regression. So now we're doing like sparse exponential loss classification instead of like sparse logistic regression, but it's almost the same, okay? But there's one big difference, which is that the exponential loss has an analytical solution for the line search at each step of coordinate descent. So when you're using features that are dummy variables, it turns out you can get an analytical solution for the line search. It's kind of a crazy formula. It looks like that, but you can actually easily calculate it. So the nice thing is if you're working on some coefficient, normally you'd have to like walk down toward the minimum. Like you start here, you want to get to there. You normally have to kind of slide down this thing and take steps down to the minimum, and maybe you pass it and go back and so on. But now this formula lets you go right from here to here. And it's just an exact formula. And it's like I said, it's kind of a crazy formula. It says like, if something is 0, do this. If it's not 0, do that. But yeah, no cutting planes, no quadratic cuts, and just goes straight there. And that makes it very fast. And so at every iteration, we just update one of the W's using the formula in the previous slide. And we use a priority queue to figure out which W's are going next. And we just keep iterating through the W's until we've converged. And we get really sparse models really quickly. Okay, so I'll go back to the FICO data set here. So our algorithm transformed the data set into 1,917 binary features, and then it iterated through subsets of them very quickly, and that is how it produced this. It chose 21 of these little step features, so 1, 2, 3, 4. You can count them, there's 21 of them, and it just chose those features in just a few seconds, and that's how it did it. All right, so far, I have talked about the Rashomon set theory, which is that simpler models exist when there are a large number of almost optimal models. And then I talked about this notion that if you run a lot of machine learning algorithms and they all perform similarly, they're all very different from each other, could be because you have a large Rashomon set. Also, if you try to predict outcomes that are uncertain, you're probably dealing with a large Rashomon set situation. And if you do have a large Rashomon set, algorithms like FastSparse can probably find a sparse accurate model. And even on competition data sets, we're finding interpretable models that people did not even know existed. And this has huge implications for criminal justice, loan decisions, and other high-stakes decisions, because in these cases, our theory makes it harder to justify the use of a black box. But I am not done yet. Now, it's worthwhile to point out here that lots of machine learning people just don't want to hear about this. Right? They're just not interested. Like these ideas about producing simple models, they're really not what mainstream machine learning has been focusing. They are and have always been focusing on building more complex models, right? Mainly for computer vision, and they're interested in preventing overfitting. So that's what they're doing. And I'm going the other way, right? I'm going more towards simple models. I don't need to prevent overfitting, right? My models are already so simple that they don't overfit, and they get a guarantee from statistical learning that they won't overfit, right? From statistical learning theory. And so it's really like a very different perspective on machine learning than what most people have. Anyway, so let us go to the next topic, which is sparse decision trees. So decision tree algorithms have been popular since the very beginning of machine learning. And the main problem that's always plagued decision tree algorithms is their lack of optimality, because they've historically been greedy myopic algorithms like CART and C4.5 that construct trees from the top downward, and then they greedily prune them back afterward. And the problem is that if a greedy algorithm chooses the wrong split at the top of the tree, there's no way to undo it. So here, if I'm trying to predict whether I'll get stuck in traffic on my way home from work, maybe rain wasn't the first question that I should ask if I want a small tree. But a greedy algorithm picked it, and so now I'm stuck with it. But the problem is that these, okay, so greedy algorithms produce suboptimal trees, but it's hard to improve over the greedy methods because decision tree optimization is really hard, right? Both theoretically and practically. There's a combinatorial explosion in the number of possible trees we could consider. And so that's why people have been constructing these kind of greedy trees since like the early 1970s and the beginning of AI. But interestingly, this has become a very popular research area lately for some reason. I've been working on it for about 10 years, and the latest method that we've produced is called GHOST, and it uses dynamic programming with bounds that reduce the search space of trees. And I'm going to just put up pictures of the army of people that we've had working on GHOST. And I just specifically want to point out Hayden and Jimmy and Margot and Shudi. This algorithm is very fast, right? It is much faster than previous approaches. And this is one of the problems that it solves, where it's trying to have the model have a low misclassification error and also a small number of leaves in the tree, and there's a trade-off between the two. So keep it accurate, keep it sparse. And when we solve this kind of problem to optimality, we get a sparse accurate tree. Like this is an example of a solution to this optimization problem on the Broward County, Florida re-arrest data. So this is the same data set that I was talking about that was analyzed in the ProPublica ProPublica article, I'm sorry. And so the tree says, well, do you have more than 3 prior offenses? If so, predict arrest within 2 years of your release. Otherwise, well, let's look at your age. Are you more than 26? If so, then predict no arrest, okay? And otherwise, then, okay, well, how many prior offenses have you had? So it just gives you kind of like, it just, that's how it works. It's all based on like the interactions between the variables. Okay, now GHOST is a dynamic programming algorithm. So it deals with lots of subproblems. So if you want to figure out like what's the optimal split at the top of the tree, then you would have to say like, well, if I chose that split, what is like, in order to figure out like what the optimal split is at the top of the tree, you'd have to figure out what the optimal split is beneath it. And then to get the optimal split here, you'd need to know what the optimal split was beneath that. And to get that one, you need to know what the optimal split is beneath that. And so it's that's the whole idea behind dynamic programming, is that you sort of solve these problems by going all the way down to the bottom and then bringing the solutions from the bottom all the way back up to the top. And so eventually what would happen is that you would get down to the bottom here and you'd be able to prove that the optimal solution for that subset of data is actually a leaf. And then you would carry that information back up to the top of the tree. All right, so so you need, it eventually is going to be a leaf, and then at that point you sort of pull up the solution to all these problems. Okay, so a subproblem is to find an optimal tree for a subset of the data, which is represented here by a binary vector. So what I'm trying to tell you is that we take the data and we represent it as a bit vector. So this is a vector of ones, which represents the whole data set. So there are n data points and there are n ones here. And that's the problem that gets solved at the very top of the, the tree. And then if you split the data on a variable, then you have 2 subsets of data. Maybe you split on some variable, and then over here you have like the first, third, fourth, sixth, and eighth data points. And then over here you have the second, fifth, and seventh data points, and so on. Okay, so it's just telling you, like, this bit vector tells you which points are in the subproblem that you're working on. And so by doing everything with bit vectors, we can actually just do very fast bit vector operations and make the algorithm run very quickly. So GHOST starts from the master problem that includes all of the data points. And then it constructs a dependency graph that holds all the subproblems that it encounters. And so here it's trying out different possibilities for the top split in the tree. Like either you could make it a leaf, or you could split on this, or you could split on that. And then beneath that, you keep working out. You go, okay, if I split here, then I could try splitting on, some other stuff. I could make this into a leaf, or I could split this one this way. So it's like all the possibilities for the top split, all the possibilities for the second split, and then so on and so forth. And for each subproblem, it keeps track of upper and lower bounds on the subproblems, and it cycles through them according to a priority queue, seeing which subproblems are solved. And then when it solves a subproblem, or when it learns more about the solution for the subproblem, it propagates that information upward back to the top. And that prevents this because this thing could get huge, right? Because you're solving so many different subproblems that this dependency graph can get really big. And so to keep it kind of small, you need to pass information up to the top fairly often, so it prevents it from growing. And then we have a bunch of theorems that also like chop off big chunks of it so that you never have to deal with it. So we prune these graphs very efficiently. So I'm going to go back to the FICO data set, which is my kind of muse today. And here is a model that our algorithm that GHOST produced on the FICO data set. And you can look at, this tree, just so you know, this is a decision tree with 10 leaves. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 leaves. And it was produced from this big data set in 8.1 seconds. And it's again on par with the best of the black box models. So you can, this tree is, it's like, achieving at the level of a black box, but it's really very, with only 10 leaves, okay? And you can look at the tree and see what it says. So it basically says, if your external risk estimate is too low or too high, then I know what your class is. Otherwise, I need to ask you some more kind of probing questions, like what's your percent of trades with the balance? And, what's your average months in file? And those kinds of more subtle questions. And just to remind you, this is not an easy data set. It's a benchmark data set, right? We didn't know it was possible to construct a single tree with this level of accuracy. And in fact, without this algorithm, I don't really know of any other way that we could have done this, because I didn't know that we could get to this level of sparsity and maintain black box performance, right? This is the kind of result we've been aiming for. And I'm really thrilled after all these years that we got there. Okay, so I hope you're getting closer to understanding the implications of the existence of interpretable models, which makes it hard to justify using black box models for high stakes applications. But there's a lot more to the story here, and there's something that's been eating at me for quite a while. Something's just broken, right? So what the machine learning world is trying to create, like with these more complex models, that's actually clearly not what the world needs right now for high stakes decisions, right? We need models that are trustworthy, that people can criticize, that people can easily double check, right? Especially for high stakes decisions, right? These overly complicated models are just not going to cut it. But guess what? My simple models won't either, because the whole paradigm of machine learning is just wrong for these problems. So let me explain. So pretty much like the universal paradigm of machine learning kind of goes like this. So you take your training set, stick it into an algorithm. The algorithm minimizes some kind of loss on the training set, and then it produces a predictive model that predicts Y from X, okay? Your model could be anything. It could be a decision tree, it could be a linear model, it could be a neural network, support vector machine, kernel regression, additive model, I don't know, whatever, okay? This is the standard approach. This is the way machine learning kind of works. You do this for essentially all machine learning applications. Even if you're doing something self-supervised, you're predicting some kind of Y from some kind of X. It's just a universal way that machine learning is set up, right? But I claim that it's fundamentally flawed. And I think we should really reconsider this whole paradigm for high stakes decisions. And here's why. So these are people that I work with. These are domain experts. I've worked with Dan Wagner on crime series detection in cities. It's used in New York City. And then this is Fides and Joseph. I work with them on computer-aided mammography. This is Xiao. I work with him on detecting heart issues from wearable devices. This is Ed and Dave, and I work with them on understanding the HIV reservoir in HIV patients. And this is Brandon. I worked with him on the 2 Helps 2B score, and we still work together on critical care. So these are patients at the intensive care unit. And these people are all very different from each other. Like, they work on all different applications. But the thing that's common to all of these people is that they've all at some point told me that I was wrong. So the thing is, when you work with domain experts and you go to great lengths to bring them a model that they can criticize, they'll do it, right? They'll say, I think something's wrong with this model. Can you build one that doesn't depend on this variable in this way? Or is there another model that doesn't depend on age so much? Or like, can you incorporate fairness constraints into your model and maintain performance? Or can you just tell me what else is out there? Just tell me what else is out there. And like, the whole premise of the Rashomon set is that there are probably a lot of good models, and there are probably a lot of good simple models too. And if that's the case, then why not just let the domain expert choose between them? And so I propose a new paradigm for machine learning, something that's more like human facing than the standard machine learning, which is to hand the user the whole Rashomon set, right? Hand the user lots of models, not just one model, and let them choose which model they want so they can pick something that doesn't just agree with the data, but also agrees with their domain knowledge or like some other knowledge of the problem that's not in the data set. And then instead of the algorithm just producing one model, right, it produces like a whole bunch of different models that achieve a low loss on the training set, okay? So this is my proposal for a new paradigm for practical machine learning. But how do we get it to work? So I'm going to show you our attempt to do this. So this paper actually solves this problem for sparse decision trees. It's an algorithm called tree farms, and it produces all almost optimal sparse decision trees. And it's pretty amazing. Like, even to find one optimal sparse tree is NP hard, and this thing finds all of them in minutes, right? Or sometimes even seconds. And it's implemented in Ghost. So it leverages Ghost's way of representing subproblems as bit vectors and its graph dependency ideas, but it also has a really interesting way of keeping track of subproblems, right? It stores all the trees in an implicit way. So it doesn't, it doesn't enumerate them, but it tells you how to combine like different parts of different trees to produce the whole Rashomon set so that you can loop through the whole thing if you want to. So even if the Rashomon set is absolutely huge, you can still store it and work with it. So I'm going to, I want to show you an interactive visualization tool that was written by this young, we have a young, brilliant human-computer interaction expert who came and worked with us to develop this, and his name is Jay. And I want to show you this. I want to show you this tool. So I'm going to stop sharing this screen, and I'm going to share it other screen. So just give me a second to work that all out. Okay, here we go. Okay, there we go. All right. Okay, so this is TimberTrack, which is an interface to tree farms. And it's storing right now all of the trees that are in the Rashomon set for the FICO, not FICO, I'm sorry. This is the Compass data set. If you want FICO, you can go down here. And by the way, this is a public website, so I'm not doing anything that isn't public. So you can access this thing the same way I'm accessing it. And what you're seeing is all of the trees that are in the Rashomon set are actually stored here. And you can search through this whole set by pressing buttons here, like I'm going to do. So let's say I wanted to just to look at the trees where the number of prior crimes being bigger than 3 is the first split. So then I can click that button and it restricts it to just those trees. So then let's say I wanted, then I wanted the second split to be people who are less than 26 years old. So I can click that. And then let's say that for my next split, I wanted to split on female. And then for the next split, I wanted, I don't know, what I can do whatever I want. And then say I find a tree that I want, then I can put it over here and I can store it. And if I like it, I can just put a little heart on it, or I can say like, I like this tree. And then I could search through and find more trees that I like, put them over here. I can kind of do whatever I want here. And then if I want to, I can display the trees by volume. So this is showing you that about 1/3 of the data points are going this way and 2/3 are going this way. And then here it's split kind of 40-60% like that. And so it's just giving you a lot of information about how the data are kind of propagating down the tree. And then if I didn't like the choices I made over here and I wanted to go back up to the top, I can just click this and it'll bring me back to the top. And I can start again and pick what the top leaf of my tree ought to be. Okay, so, and yeah, like I said, I can keep as many trees as I want. I can organize them into little piles or whatever I want to do when I'm sort of looking through the Rashomon set to pick my favorite model or whatever. All right, so let me go back to the other screen here. Okay, great. So yeah, like now we can hopefully provide something that is more useful to practitioners. And this is where I think we should be focusing, right, on these more kind of human-facing questions for artificial intelligence. All right, so just to summarize, I talked about the Rashomon set theory. I talked about fast, sparse, and ghost. And yeah, I just wanted to point out again that this has huge implications for criminal justice, for loan decisions, and for other high stakes decisions where we have to use data to make decisions in society, because now we really can't justify the use of black boxes. And I think this has huge implications, particularly if we can provide users the freedom to choose between the different models. Thank you very much.
That was fantastic. Thank you so much, Cynthia. That was amazing. That was amazing. I have a number of questions here. I could read them to you if you like. So from Ramachalapa, is Bayes' information criterion or its variant useful for identifying the sparse model?
No, we don't use that because that's like a heuristic for like inclusion of features, and our algorithm fully optimizes the collection of features. Our algorithms fully optimize the collection of features, so they don't need heuristics like that. So it says, nope, find me the best model that's sparse and accurate. It just uses those two criteria, and like you can use like BIC and other AIC, those other things. You can use them when you can't solve the combinatorial problem and you just need to like eliminate variables. But we actually solve the combinatorial problem, so we don't need that.
Okay, thank you. Lonnie Chrisman asks, let's say you use 100 simple Rashomon models on a problem, and then look at the fraction of them that predict yes. Under what circumstances would that frequency work as a probability of being correct? Would the algorithm for generating all Rashomon sets need to be tuned to obtain this property, or do they naturally tend to make statistically independent errors? Okay,
that's a good question. So I think he or she, sorry, I can't tell, but I think this person is asking about the sort of characteristics of the models inside the Rashomon set, and like, do they all predict the same way and stuff like that. And so I actually have exactly one extra slide that kind of tries to get at that, the answer to that question. So I'm going to answer that bigger question that I think they're asking. So what I'm showing you here are, okay, let me explain this. So if you take the whole Rashomon set, you can calculate distances between models in different ways. So I've calculated the distance between models in 3 different ways. The first way is tree edit distance. So in other words, how much do I have to edit one tree to get the other tree? And then the second distance that I'm looking at is prediction set distance. So this is like, how different are the predictions from one model to the next model, right? And then the third distance I'm using is feature set distance. So that's like, I list all the features in one model and I list all the features in the other model, and what's the edit distance between those? Like, how many features do I need to omit from one model and add in from the other model? Okay, and that count of that is this feature set distance. And then we took all of these, so what you have now is a graph, right? Because you've now graphs, and you have all the trees that are different from each other by different types of distances, right? So you can take high dimensional graphs and then project them down onto low dimensions, onto 2 dimensions, using a dimension reduction algorithm. And so this dimension reduction algorithm I'm using is called PackMap, and it's designed to preserve kind of graph structure. So when you project everything down, you get to keep the kind of graphical structure. So the dimensions they don't mean anything, these dimensions. They're just a projection. It's like you're looking into high dimensional space and kind of seeing what the Rashomon set looks like. And so here's like a couple of different, so this is 3 different ways of viewing the Rashomon set. And the different dots are show you the top split in the tree. So you're seeing that the Rashomon set has a lot of trees that have different top splits. So we have like a, you could pick this feature as the top split, which is smiling, or you could have a split on is jacket color red, and then this light blue one is like holding sword. This is a game data set, so it's got kind of fun features. And then if there's a blue circle here, it means that I'm showing you the tree over here. And then a red circle means that it is like one of the most accurate models, like it's very, very accurate compared to the others. And so what you can see here is that when you look at things like prediction set distance, there are really 2 clusters with a manifold in between them. Like there's like this cluster that kind of predicts similarly, and then this cluster that kind of predicts similarly. But there's all these models, they all predict slightly differently from each other, right? So that's something that's kind of interesting. Like they don't all predict the same way. So, if you think about like the fraction of them that predict yes on a specific data point, maybe it's not as high as you think, right? There's a lot of variation in the predictions of the different models in the Rashomon set. And there's also a lot of differences in the features that are used in the models in the Rashomon set. So it's actually kind of neat to get this kind of bird's eye view of what the Rashomon set is actually doing. So I hope that I've answered your question. And in other words, I don't know what frequency for any particular Rashomon set, but I can show you what the Rashomon set looks like, and you can do these kind of calculations is what I'm getting at. Okay, should I go to the next one?
Yeah, so Kevin Duh asked, the idea of Rashomon set is exciting. What hypothesis spaces can you compute the Rashomon set in a reasonable amount of time? I understand you can do this for sparse decision trees, but how about logistic regression, support vector machines, or neural networks?
Okay, so we haven't managed to do those ones yet. We're working on some other Rashomon set calculations. Decision trees was the most natural one since we had already gone to the trouble of creating Ghost, and so it was a natural extension for doing that. Decision trees is actually a very big space. Like it's actually quite an impressively large space. So it's it's kind of hard to get the Rashomon set into it. You can get the Rashomon set very easily for something like linear regression. We have a calculation for that in the paper with Lesia and Ron, because it's just an oval, right? It's just like an oval in high dimensional space. And support vector machines I'm really not interested in for several reasons. First of all, they don't work because you have to choose the kernel, and that kernel may work for one part of the space but not another. And so SVMs just tend to not be reliable in more than 15 dimensions. And so I've sort of the beauty of the convex optimization in SVMs is kind of worn off to the point where I don't ever use them. So I'm not really interested in that. And then neural networks it's almost impossible to calculate. So I don't know how to get the Rashomon set for neural networks. But sparse logistic regression, we're working on that. If you're not interested in sparse logistic regression, it's convex, right? The Rashomon set is actually a convex chunk of feature space, and so you can get it. It's not too hard to get it, and there's actually kind of old time calculations for doing that. But I forgot the name of it's like the second derivative of the logistic regression. It's a very classical thing that if I taught statistics yesterday, I would know the name, but I just forgot off the top of my head. But there's a way to get it for logistic regression because everything's convex. Yeah.
Okay. Are there any other questions from the panelists?
It's not a question, but I see one that just popped up in the Q&A.
Oh.
Lonnie said this was an exceptionally good talk. The presentation was excellent. The results were impressive. I learned a lot. And Kenny said thanks.
Thank
And
you.
I think I wanted to open up to the room here as well and see if anybody has questions here.
Well, I'll just, so this is Jim, and so I'll echo that fabulous talk. Thank you so much for taking the time to pull together what was such a fabulous introduction to the topic. So my question is do you have can you sort of walk us through any case studies of actually of experts navigating the Rashomon set in order to select their favorite sort of decision tree? How do they actually do that? What are they kind of talking about and thinking about as they're working that? And because I can imagine it being pretty complicated the first time, right? As they're sort of struggling to understand what happens, and then maybe getting a little easier. I don't know. Just curious how that actually works.
So the paper that I presented, the tree farms paper, is very recent. Like it only was accepted like a month or two ago. So it's very, very recent. So it is, hasn't had its turn yet in practice. I can tell you how we created the 2 helps 2B score though. So that one, we have an algorithm that produced scoring systems, which are sparse generalized additive models, right? And this algorithm, you could fiddle with a parameter and have it produce a bunch of different scoring systems. So we actually printed out a packet of about 100 models, and our domain expert, Brandon, he's just amazing. He actually went through them and like picked his favorite. Like it was just, it was like the printout of the Rashomon set, and like going through it like, oh, I don't like that model, I like this model, I'm gonna move that model over here, and just moving paper around. And that's what we wanted to kind of avoid here. We wanted to give people like an interface so that they could sort of interact with it. So it hasn't gotten its time in use yet, but I think it's going to be much easier for the domain experts than just printing out a giant pile of these things. But I'm not sure. Well, I mean, we have another algorithm that is that also was accepted recently in the same NeurIPS 2022 pile that it also generates tons of scoring systems, and we don't yet have an interface for those. So this is all work in progress, and this is where I think the future of the field's going. So I haven't answered all the questions yet.
Well, I guess where I'm kind of coming from is this a way to sort of probe how the experts are actually thinking about the problem? Maybe sort of tease out sort of subconscious, judgments that they're bringing to the problem that they don't articulate. And I'll mention this because we have a project which is about sort of using AI to help understand how expert teams work. And this just seems to be a very interesting, if you kind of turn it on its end, this is kind of a probe to how they're thinking.
Well, that's the idea, right? That's exactly the idea. Is like they go, okay, I don't want this whole class of models, so I'm just going to get rid of that class, and I'm just going to look at these models over here. Yeah, I mean, lately the domain experts have given me sort of, to be honest, the most recent kind of feedback we've gotten on a set of models that we gave them was, oh, that whole class of variables, you shouldn't use that. Just get rid of it. So,
wow. Wow.
Yeah.
Wow. Well, thank you. I'll let other people here ask questions.
I know, Tony, did you have something you wanted to discuss?
Well, thanks, Cynthia. Excellent talk. Really appreciate it. If one has an imbalanced data set, does that have any bearing on this, or is it pretty much this is only as good as what you're given? For example, I'm working on a project with people in the School of Medicine on predicting fall risk for patients in hospitals, but the falls are few and far between.
Right. So
are there any tricks that this might uncover?
There are tricks. Okay, so there's a theorem in the tree farms paper that says that if you want the Rashomon set for a weighted accuracy or a balanced accuracy, right? So you would want something like balanced accuracy because it's balanced between the classes, right? You're looking at the two classes equally. If you want a balanced accuracy Rashomon set, you can get it by calculating the regular Rashomon set for a larger Rashomon threshold. And then the balanced accuracy Rashomon set is inside it. So it's interesting because you can actually get the whole Rashomon set for balanced accuracy inside the one for regular accuracy if you bump up the threshold. Also, Ghost, I did not get a chance to say this because, you know, I couldn't say everything, but Ghost is actually generalized. So the first letter in Ghost is generalized, so generalized optimal sparse decision trees. And the reason it's called generalized is because you can put in your own loss function. So if you wanted to put in some kind of balanced accuracy or weighted accuracy, or if you want to have like to maximize precision subject to this recall, or if you want to put some kind of constraint on the false positive rate or whatever it is, you can just put that directly into Ghost and it will solve that problem that you are interested in. So that's what makes it, and it makes it good for imbalanced problems. It also can optimize AUC. There's also a version of Ghost that optimizes AUC. That one's a little bit slower because you got to look at, you know, it's a rank statistics, so you have to look at pairwise stuff. But if you want to do something like, you know, optimize optimize the number of, or optimize the false positive rate subject to this constraint on false negative rate, like Ghost can just do it already.
Excellent. Thank you. We'll take a very close look at the work. Appreciate it.
Sure. And then fast sparse also, since it's using exponential loss, it's already optimizing AUC. So it should be okay for imbalanced data set. If it's not too imbalanced, it should be okay.
Thank you.
Cynthia, predicting the future, do you believe you'll be able to extend your work to all types of machine learning, or will there be certain limitations?
Well, I mean, I'm not even going to try doing neural networks. I think neural networks are just a giant mess. So, you know, I'm just happy enough to get a neural network that's actually interpretable, and, you know about that. So, yes, so we're not even attempting that. Yeah, to be honest, 10 years ago, I never thought we would even get to the point where we got to with Ghost. Because I was like, there's an NP-hard problem just to find one optimal model. How is it that we can find all of them in seconds? Like, how is that even possible? So I didn't even think we could get there. So taking baby steps over a long period of time seems to work just fine for me.
That's great. It looks like you're on the verge of changing the machine learning paradigm for civilization.
I hope so, because I think it'd be better. It'd be more helpful to people doing high stakes stuff.
I know we're over time, so I just wanted to say thank you once more. One last question just popped up from Donald Duncan. He said, any potential application of these techniques to LLMs?
What's LLMs?
Large language model.
Large language model?
No, I don't think these are the right types of models for I don't think these models are large language model appropriate. I think you probably would need to define what interpretability means for large language models. For language, sparse models don't really work. Sparsity is not an interpretability constraint. So for language, you'd have to define what you think is interpretable. So I don't work on natural language processing because it's just not my area. I'll work in computer vision, and I know kind of what I think is interpretable for computer vision, but for large language models, I don't know what it really means to be interpretable.
Wonderful. Well, thank you. Everybody, thank you for joining. Dr. Rudin, again, thank you for a fantastic talk. And we will hop onto the other Zoom to close out with you if you're free.
Yeah, that's fine. I just hope I can find the other Zoom link.
I can resend it.
Okay,
all right.
That's great. Thank you.
Thank you all so much.
Thank you.
Take care. Bye, everyone.